All right, good afternoon, everyone. Thank you for joining us today. We're going to wait another minute or two to give everybody a chance to join. We'll start shortly. Good afternoon, everyone. We're getting started shortly, about another minute or so. We're just waiting for everybody to have a chance to join. Thanks. Good afternoon. Let's get started. My name is Ben Hartzell. I'm Vice President of Marketing at GMW, and I'll be your facilitator for today. Thank you for joining us. I'll introduce our speakers in a moment, but first a few logistics. Everyone should be muted already. If you have any questions, please use the Q&A box. We'll have a question and answer session at the end. This webinar is being recorded. We will distribute the recording to you within a few days later this week. It's my pleasure to introduce our speakers and outline our agenda. First will be Jenn Gannon with Computational Physics. She will start us off with an introduction to space weather and impacts on man-made installations. Following will be Letourneur, Senior Applications Engineer at GMW Associates. He'll introduce fluxgate magnetometers for monitoring variations in the Earth field. Then Mike Henderson, owner and engineer at GIC Magnetics, will outline a system integration for hardware through data processing and key concerns to be aware of. We'll then return to Jenn for use of data for GIC monitoring and prediction in power networks, as well as upcoming regulations to be aware of. Then Ludo will speak to magnetic data and magnetic storm monitoring for the oil and gas industry, particularly for directional drilling. And finally, Ludo will have answer the question about what's next. What other channels can we add to our data stream, such as current monitoring? Then we'll close out with Q&A at the end. If you have any questions for someone in specific, please mention who the question is for. Otherwise, I'll do my best to field it to the best candidate. And Jenn, off to you.
Thanks, Ben. I love doing the space weather intro for these things because it gives me a chance to go through the NASA public image library. Ben, I don't think this is advancing. Oh, there we go. Yeah, so if anybody's ever looked through the NASA image library, they've got some beautiful stuff. So the next few slides that I'm going to show are borrowed public domain images from NASA, particularly of the sun. And you know, the reason we're talking about magnetometers is that the magnetic field is really the driver of everything space weather. You know, space weather is the interaction between the sun and the Earth, and everything from the roots of the driver on the sun all the way through the man-made installations and the power grid impacts and the directional drilling impacts on the Earth is driven by the magnetic field. So things like solar activity, flares, sunspots, CMEs, solar wind, the magnetosphere, ionosphere around the Earth, and the very complicated interaction between them, the radiation belts that surround the Earth, the Van Allen radiation belts that are rings of particles that surround the Earth, the aurora. These are all parts of space weather and all parts of the drivers of what we experience on the ground as a geomagnetic storm. Going back to the sun and the magnetic field, the sun is massively complicated. It's massively complicated, it's massively large, and it's complicated from the magnetic point of view with complicated magnetic structure. It's not as simple as the Earth's magnetic field. It can sort of be modeled like a dipole. It's got loops and tight areas of magnetic field density. It's very, very complicated. There's the sunspots that travel from the northern poles down through the center. There's differential rotation, and all of these things produce effects that can impact the Earth. So again, another one of these beautiful NASA images on the left shows a prominence, which is a magnetic field loop where plasma is funneled along that magnetic field loop, and so you can see it in this illustration. You can also see that the relative size of the Earth compared to that plasma loop on the magnetic field, and it's massive scale. So when we're talking about large storms and large space weather effects, CMEs are often mentioned, coronal mass ejections. And a coronal mass ejection, you get something like this complicated magnetic structure, like a loop, that becomes so complicated at the base, it splits off from the sun and ejects into the interplanetary medium through the solar wind. So that magnetic field twists back on itself and shoots a bubble off that includes this highly charged plasma going very, very fast through the solar wind. So these are some images from probably SOHO that show actual CMEs. I think this is a large CME in 2000 that didn't hit us, but if it had, would have been an extremely large magnetic storm. There's a lot of uncertainty in this. You know, we're a tiny little dot in the plane of the sun. And so whether one of these things is directed towards us or not, there's a bit of uncertainty. And even when we measure it, there's uncertainty in whether it's going towards us or away from us. You know, can you see that from a two-dimensional image? So say this thing is heading towards us. Now you have a ball of plasma 100 times the size of the Earth barreling through the solar wind at 2,000 kilometers per second, very fast, very hot, and it hits the Earth. That sounds bad. That sounds really bad. That sounds like a Bruce Willis movie bad. Luckily, we have a magnetic field of our own that shields us from this plasma directly hitting the surface of the Earth. Instead, what happens is the plasma and the magnetic fields associated with that plasma hit the front of the magnetic field and compress it. Or there can be other complicated things like reconfiguration and realignment of the magnetic fields. That magnetic field protects us from being directly hit by these CMEs, by this burst of plasma from the sun. And when the front side of the magnetopause or the magnetosphere or the magnetic field of the Earth is compressed, it causes a lot of complicated interactions and a lot of cascading interactions to happen. New current systems form, the radiation belts grow, the magnetic field lines on the back side of the Earth loop around, or on the front side of the Earth loop around to the back and bring with them particles that then travel down the magnetic field lines to the poles and produce aurora. And the magnetic field of the Earth is reconfiguring and changing very, very rapidly. Oh, and actually I have a movie. This is a beautiful NASA movie. That shows the CME barreling towards the Earth, hits the Earth, compresses the front side of the magnetic field. This is an effect called reconnection. And all this results in the beautiful aurora and the reconfiguration at the surface of the Earth. So when this happens at the surface of the Earth, we can get some of these beautiful effects like aurora and things that you can see, and you can get some not so beautiful effects. You can get the potential effects on the power grid, on man-made infrastructure, on navigation, on directional drilling, on where airlines can fly. You don't want planes flying through particles precipitating down through the poles because of radiation issues. So there's beautiful visual effects and then also some hazards that can occur to this. And storms occur fairly regularly. Large storms, not so much, but they're things that have happened and that we've had near misses and that we expect in the future. Now, when the fields are changing on the ground, we know that when there's a rapidly changing magnetic field from Faraday's law, there has to be an induced electric field. But it's made more complicated because that magnetic field is changing in the presence of a spherical conductor, which is the Earth. And the Earth, that the presence of that conductor makes the induction of the electric field a little more complicated. And to make it even worse, the Earth itself is not a simple spherical shell or conductor like you'd see in an E&M class. It has layers of different resistivity, conductivity. It's got different regions of complex geology from different points on the Earth. So the effects of space weather on the ground due to these changing magnetic fields can be very different from place to place. And knowing the local conditions can be very important. So measuring these changing magnetic fields is critical to understanding what's happening during a geomagnetic storm or geomagnetic disturbance. And with that, I'll pass it off to Ludo.
Thanks, Jen, for the introduction. So what I'd like to do now is spend a bit more time talking about the fluxgate sensors, which are the center of the magnetic field monitoring system. So I'm just trying to skip slides. Okay, there we go. So we use typically fluxgate sensors for measuring the magnetic field of the Earth. They are a vector component sensor, so they measure the magnetic field along the direction of the fluxgate element. So typically you will have a 3-axis sensor to reproduce your north, east, and down components of the field. And because of their characteristic in terms of measuring range and ability to measure very small sub-nanotesla field variation, they are perfect for monitoring space weather activity. Typically, the Earth's field will be around 40 microtesla, 40,000 nanotesla, and space weather can add anything from a few nanotesla to a few hundreds or thousands of nanotesla. You can see from the data from on the left from March 1989, the field variation could be up to 1,000 nanotesla or more. For space weather, and especially for GIC impacts, what is the main driver for the occurrence of GIC is the field variation over time rather than the absolute amplitude of the variation itself. So something that can respond with a bit of speed is a useful sensor to have. So if we look in a bit more detail about the fluxgate, fluxgate is typically a piece of hypermobility core material with an excitation winding and a pickup coil wound around it. And there are different topologies for fluxgates, ring core, single linear cores, or twin linear cores. And I'll talk a bit more about the twin linear cores, which is the type of sensors used by Bartington. So if we look at on the left-hand side, typically you have two pieces of core material, hypermobility, with an excitation winding around each of them. The winding are in opposite direction, so that when we apply our excitation signal, one core reach saturation in a positive manner and the other one will be negative. And then around that, we have a pickup coil. So as I mentioned, we'll drive the fluxgate with a square wave most of the time, which will bring saturation. And if there is no external field, that saturation happens synchronously on both core materials, and there is no induced voltage within the pickup coil. On the other hand, if there is an external field, one core reaches saturation before the other, and we start seeing an induced voltage within that pickup coil. So that induced voltage, lights off automatically. So that induced voltage is could be measured directly, but in most cases, it is used to drive a feedback current into the pickup coil. And what we're measuring is the intensity of the feedback current through a scaling resistor, through a precision resistor. And that gives us our voltage output of the field amplitude. Using that closed loop, that null mode, has a few benefits. It increases the linearity of the system and increases its sensitivity. So now if we look a bit more in details at the Bartington fluxgate sensors, there's quite a range of sensors, and most of them will offer noise level in the tens of picotesla or less. So they are extremely precise instruments, and they can detect very small variations from things like vehicles at a fairly long distance. So one of the elements to take into account when setting up a network of magnetometers is finding a suitable site away from man-made interferences, railroads, roads, fences, or anything that is ferromagnetic and subject to movement. Mike will touch on that on the hardware side of things. Something to also take into account is temperature variations. Sensors will be subjected to some temperature drift, and because they will be deployed for long periods of time in the field, you want to be able to either limit the temperature changes by insulating the sensors or having access to a temperature sensor to perform some compensation. The Mag13, which is one of the most suitable sensors for the work, has very low offset, very low noise, and a temperature sensor that can be used for the, that compensation. Again, Mike will touch on that. So they are, in general, the sensors are extremely good. They have very low offsets, and those offsets are stable over time. So they don't impact on the precision of the measurements. As we're looking at field variation, we're mostly interested in field variation rather than absolute field measurements. So in addition to the Mag13, there are some alternative sensors. If you had, for example, a requirement for lower power system, sensors like the Mag649 will offer much lower power consumptions. Or if you have cost-critical installation, sensors like the 690, whilst they will have slightly loosened performance, will allow for cost reduction. But that range of sensors are all very suited for field deployment, offer some environmental protection, fairly compact, relatively low power compared to some other types of magnetometers, and are ideal for deployment. So in addition to the work that Computational Physics has done and GIC Magnetics have done on deploying the sensors, there are a few others that have used Bartington sensors, and all that information is in the public domain. So Australia has deployed a network of sensors for space weather monitoring, and they've used the Mag03 for a fairly long time now. And here are some examples of their installation. And more recently, USGS has been using the Mag690 for installation with their seismic sensors in Alaska, where to monitor space weather activity and to try to reduce that impact on the seismometer noise that was observed. So again, that was published last year, and here is the link to the publication. So I will now pass on to Mike, who will be looking at the hardware implementation in more details.
Well, hello everyone, I'm Mike Henderson. I'm the owner of GIC Magnetics, and we have been integrating these fluxgate magnetometers into measurement stations for the past about 5 years. We've got 15 deployments that we've done in about 9 or 10 states at this point. And I'd like to talk about the practicalities of using an instrument like that in a network. And maybe the most important thing I can emphasize, at least as I approach magnetometers versus other things I've done, is that a magnetometer is really not just another sensor like a thermometer or a pressure meter or something like that, where you can kind of grab the data at a regular cadence and store it and just use it as is. The magnetometer, as Ludo said, is extremely sensitive to the environment, and it really needs a little foresight and planning to make sure that it works effectively for your application. When I say it's sensitive, I mean, if it's sitting on your kitchen table, you're going to be able to see your garage door open, your neighbor's garage door open, cars entering the neighborhood. And we'll talk a little bit more about the sensitivities in a moment here. In the deployments, some of them were kind of wooden post, simple things to begin with. And now a lot of these systems are MagStar, which was developed in conjunction with CPI. And they are deployed from the sort of the Canadian border at the north down to the Gulf of Mexico and Texas. So we have them in a number of locations. Let's see if I can advance the slide. Okay, so the main culprit in creating a good environment for a magnetometer is iron. And the rules are pretty simple. The bigger the iron, the worse the problem. And the more the iron is moving, the worse the problem. So you can have a magnetometer located relatively close, relatively to a stationary piece of metal that isn't too big, like part of a chain link fence. Looking at cars moving or a truck, worse, a semi, something large, are going to need to be further away. And I say further, I'm thinking of 300 feet or further. You may be able to detect it, but it will cause problems if it starts to get closer than that. Something like a train, at least twice as far. So I would say 600 feet or further for something as large as a train. The picture on the left is a MagStar. That's aluminum construction. If you're wondering how that's sitting there, nothing over there is, of course, ferrous. So your construction materials are going to be plastics and aluminum and brass. Once you've found a location that's quiet, and keep in mind, I guess, that quiet now and quiet in the future. So you want to pick a piece of property, if you can, that not only has nothing around it, not where cars are going to go, but where no one's likely to want to move something in the next 6 months or year. Otherwise, you have to ask them not to do that or try to move your station. So desolate areas that no one wants to use are excellent places to consider putting a magnetometer. Deploy them at the end of emergency airstrips or in rice paddies, or one location was where the bomb squad tested their munitions at the University of Illinois. So no one wants to go there. It's a good place for quiet magnetometer operation. But when you get it in that quiet location, the effect of a moving piece of metal is similar to the effect of the sensor moving. So be aware that the sensor has to be motionless. I had one on the floor of my concrete office, which has a thin layer of wood flooring over it. And as I approached it, I couldn't get within 2 feet without seeing noticeable disturbance. So even small amounts of physical vibration will show up in the signal. The device needs to be mounted level, and it's, I guess, easiest if you orient it towards true north, that's to say the axis of rotation of the Earth, rather than magnetic north, just so you don't have to rotate the data later to have it line up with the grid. So make sure it's low. In our case, we use a 3 to 5 foot pillar of concrete that's 14 inches in diameter. So it's a multi-100-pound slug of concrete in the ground that will heave only like a piston and keep that orientation level during the winter months and over year to year with soil expansion and those kinds of things. As Ludo said, there is a sensitivity to temperature on the flux gates, and this has to be kind of handled in one of two general strategies. One is an insulation, so you can build an enclosure around it and insulate that, or you can try to bury it in the ground if you can make sure that no water gets in. Another approach is to use the built-in temperature sensor, for instance, in the Mag 13 that Ludo mentioned. On the left there, you can see a couple of plots. That's a Mag 13 uncalibrated, and the USGS Observatory, also here in Boulder, Colorado, which is kind of the gold standard for magnetic field data. And the blue line is just the ambient temperature of the sensor as the days go by. So it's like 3 days of data. And you can see the two graphs, they resemble each other, but they're not really right on top of each other. On the right is a calibration of that same data, taking into effect the blue temperature line. So this is a single term that just scales the Mag 13 data to agree with a calibrated source. The bad news of this is that this has to be done on each sensor element of the Mag 13, and each magnetometer is different. So the process is that you calibrate the X and the Y and the Z separately, and you make sure you do that on each magnetometer. So make sure that you get the data accurately. The nature of the magnetic field that we're trying to observe is over a large area. It could be as large as the United States, or it could just be as large as your footprint of interest. But in any case, it isn't going to be a single sampling system. And so if you're trying to combine your data with that of another network, or even two stations which are remotely remote to each other, for instance, the one in Canada and the one in Texas, you need to concern yourself about getting an accurate time representation of the data. So the easiest or most tempting way to do this is to record that time at the collection point, at the server. But in that case, you'll run into the network timing jitter. So the communication paths differ. Someone may be streaming Netflix at the office that the server's at, and suddenly you get delay. And what is supposed to be 12 noon for one sensor is not 12 noon for the other. So the best way to handle this is to synchronize the sensors with GPS so that they're timestamping the data with that UTC reference right there at the source, and then you don't worry about the propagation delay through the network. So how much power do you need? Once you have it remote and it's far away from a building, the most convenient way to power it without making a big trench and hardline cable is to consider solar. So for the MagStar system, the power has been minimized to around 6 watts. And so 6 watts is about what your cell phone, your smartphone takes when it's charging. So when you plug it in at night and it's getting its batteries restored, that's 6 watts of power. Keep in mind the effect of the winter solstice in the north, and especially with snow and cloud cover, actually makes that 6 watts require a 360 watt solar power system to operate reliably with multiple days of snow. Obviously, that's not what it needs every day, but just to make sure that it's continually on and can manage a storm collection during a physical snowstorm, a 360 watt system is what we found helpful or useful to make that operate continually. And that's about 180 pounds. So the bad news there is that if you went from a 6 watt to 12 watt or to a 24 watt system, you're talking about a scaling of that solar power system commiserately. So it can get pretty big. So you want to keep that power down. Now, if you're in the southern latitudes and you think that is not a problem, you have the other one to worry about, which is summertime deployment. That 6 watts is a heater. So when it's in an enclosure in the summer, it's going to tend to want to heat it up. If you don't want a forced air system that could bring dust into the enclosure, then you want to keep the power down as low as you can. So another aspect of the remoteness of the sensor is the need to get the data from the sensor to the server. And there's kind of two aspects of that I'd like to talk about. One is just the physical connection. How do you get the data out? You can use something like a point-to-point Ethernet connection. We've used Schweitzer 3060 point-to-point Ethernet modems, and those work well. If you have a building with like internet connection that's within a mile or two of it, line of sight. The other option is to use a cellular link. If you do use cellular, then don't plan to go into your local mall store and buy a SIM card from whoever's selling them there. What they will give you is the standard SIM card that would be useful for a person, but you need an M2M or machine-to-machine account. So the signature of that data flowing continually looks a little different, and the network eventually gets alarmed and will shut it off. So you actually need an M2M account to get a cellular backhaul. The other thing to consider is that the remoteness of the magnetometer makes them a little bit vulnerable to physical security problems. So obviously you could have vandals, someone may come by and vandalize it or even use it as target practice. But the bigger concern might be physical compromise of the unit from a network security point of view. So if your sensor has lost physical security, you need to be thinking about what would happen to the rest of your network from a cyber point of view. So what we have done is we geofence the station so that if it's not in the spot that it's supposed to be, it simply doesn't communicate, and we can revoke the security credentials from the box remotely and keep the rest of the network up. So it's just kind of something to think about when you are off in a remote spot, is that you may not get as much physical security as you would if you were installing in a brick and mortar building. And in fact, we had one of these stolen from a station kind of near the university here in Boulder. And it was, I was thinking it's probably just someone, who'd been camping in the area, but if it was a CU computer science student, we're still safe because they can't get into the network from there. And lastly, I'm almost done here. You need to be able to store the data. Just a few things to consider is that you probably want to limit people's access to read-only. You know, once you collect that data, you don't want to get another chance to get it. So make sure it's read-only. And the data rate for a station might be around 8 gigabytes per year. By today's standards, not huge. It does grow. You know, if you have 6 stations and you do this for 5 years, it's going to start to get there. But it's not something that is a massive data storage problem right now. So I've been talking about the MagStar system, and this is kind of the physical implementation of the basic concepts that I've been discussing. And this has a few more kind of practicality features just for permanent and autonomous deployment. For instance, the pole can withstand 90 miles an hour of wind. And we actually had one, I think it went through Hurricane Laura this year on the Texas Gulf Coast. And I still sit on my front porch and just watch the temperature drop from the station logged in. It has like a redundant sampling system so that each measurement gets flagged as valid or invalid or suspect in case some sort of environmental problem occurs near the station. It has an alarm system. So stuff that's just kind of made to make it work well from an autonomous point of view. And later on, if you have any questions about the deployment or capabilities of this, I'll be happy to answer them. And I think I am done. So on to Jen. Thank you.
Thanks, Mike. Okay, so now we know that measuring magnetic fields is important, and we know we can do it accurately, and we can do it well, and we can deploy systems remotely. How does this help power system operators? So the next few slides, I'm going to go through specifically some applications for power transmission and power system operators. And you know, we've known since the 1989 Quebec storm that there can be a significant space weather effect on power systems under certain conditions. I mean, understanding what those conditions are is key to mitigation. So the Federal Energy Regulatory Commission has put into place a set of requirements under regulation TPL 007 for power utilities with these assets to address these planning needs. And I'm not gonna go through all of TPL 7. It's a fairly long regulation. I know we're all extremely excited about regulatory and compliance, but I'm going to focus specifically on the 2 elements of TPL 7 that have to do with measuring magnetic fields. And first is the requirement to use the magnetic field data. So to have a source of magnetic field data or to measure it locally, and also measure the currents in the system. The reason for this is to know your local hazard conditions, and also to use it in model validation, which is a second requirement in this planning phase. So I believe last I heard the requirement to ingest magnetic field and GIC data was due July 2021. Don't quote me on that. Please check your regulation, make sure it's not changed. The next step after that involves magnetic fields is the model validation. So model validation is where you take your inputs that you've measured, you use your system model to try to reproduce what you've seen in your system during that time, and make sure it matches your measurements. So you're taking your magnetic field driver, you're using your models, and you're trying to make sure it matches the response, the GIC response in a transmission system. And the reason to do this is that accurate models mean that your planning scenarios are also accurate. So if you're trying to plan for a worst case scenario, you need to know that you know, everything that you've got will be realistic during storm time conditions. So just briefly and high level, I'm happy to talk to anybody one-on-one. If you want to reach out to me by email about any of this. The model validation steps. Step 1, measure the magnetic field and the GIC at the same time, preferably at the same location, although that's not always possible. during an active period, particularly during a large active period, during a large geomagnetic storm, so you can get a good signal and see how the power system responds to a large event. That's hard to do. You can't just order large storms. We haven't had any in a while, but I'm sure we'll have some in the future. You take that magnetic field, you calculate the electric field from your magnetic field and from your Earth model. You plug that into your power system to estimate GIC, and then you compare your measured with your modeled, and if everything matches, you know that your models are right and your planning scenarios are solid, and you can plan around large events and do mitigation for any potential large events. I'm including a reference. Most of the next few slides are coming from this EPRI model validation guide, which is publicly available on their website. I'd highly suggest taking a peek at that if you want a little light 150-page reading of technical details on geomagnetism. I'm going to go through each of these steps briefly and kind of give some best practices. First, measuring the magnetic field and the GIC. We're focusing here on magnetic field. There's lots. There are lots of complications and things to consider when doing GIC measurements as well. But for magnetic field, the best practices are to have 10-second cadence or shorter measurements. Remove spikes in bad data. Most of that's environmental noise, so that goes back to placement of the sensor. A large spike in your magnetic field will give you a false large spike in your electric field, which will give you a false large spike in GIC, and you don't want that. You only want to analyze real information. So spikes, particularly from environmental noise, can be really important for transmission planning. And you want the magnetic field measurements to be as accurate as possible to your local area. There's not solid guidance on this, but multiple analyses are kind of converging on the idea that if you have the magnetic field within 150 or 200 miles of your GIC measurement, you can get most of the variation, although you won't get some of the high frequency information unless you're really close. Calculate the electric field. This is complicated. There's a lot of discussion that goes into this. There's 3 different methods for doing this that are discussed in the regulation and also in these upper reports that I'm referencing. They start with scaling factors, which are really just real high level. They're just indicators of how hazardous one region is compared to another. So one step in the planning regulation is to use these scaling factors, but there are more complex methods that can get you more accurate local results. And they go from 1D uniform electric field models to non-uniform electric field. And again, I'd refer you to this EPRI paper, as well as there's a bunch of published literature on all 3 of these kinds of methods, or feel free to reach out to me if you want more information. Estimate GIC using your electric field. So once you've calculated your electric field from your magnetic field, you need to put it into a system model. Most of the system model software right now, I believe, can take some form of the electric field. We predominantly use PowerWorld. We've used PowerWorld fairly extensively for the model validation work that we've done. I know it can ingest the electric fields pretty simply. I think PSSE can as well. They may use voltages instead of, or potential differences instead of electric fields. I'm gonna mention this next bullet. This sounds really dumb as I'm saying it, but I'm embarrassed to admit how long it took me to figure out some of the interface here between the geophysics world and the power engineering world. That the geophysicists, space weather folks, use kind of a strange orientation system. X is north. A lot of the power system modeling software, X is east and west. So as you're doing this, just keep that in the back of your mind. It's not an important detail, but it could save you a lot of time as you start doing this. And then you want to compare, measured, and modeled, making sure you have good data, both on the input side, the magnetic field, and on the validation side, the output side. The GIC data will make your life much easier. But don't expect a perfect point-by-point match. This is an evolving area of research, and there are a lot of uncertainties at each step. So Here's an example from that EPI report that I mentioned. We consider this a decent match. This is measured and modeled GIC in a system. This is published in this report. You can see how we got to this tiny little event here, but this is considered a good match because the modeled GIC at the peak is pretty close to the measured GIC at the peak. This was because we had really good magnetic field data from the Fredericksburg Observatory. We had some good ground models and a very good system model, and we were able to reproduce these. In addition, the model is a little higher at the peak than the measured. That's gives you kind of a conservative answer, so you want to make sure you're getting the worst case scenario in your planning situations. This can be considered a decent match, even though it is a fairly small storm example. This one not so good. In actuality, that black line is the measured in the system, and the green line is what was predicted. Under this, we needed to do some corrections because this is a model validation case that didn't work out so well. Now, I can't, of all the model validation runs that we've done, very, very few of them match really well to begin with. Like I said, there's uncertainties at every step. Here's the top three that we've run into. If you're trying to use magnetic field data to do a model validation, number one, system your substation grounding values have a huge impact on your result. Maybe you've measured the substation resistance, and that was 40 years ago, and it's rained a lot since then, and there's corrosion on your grounding mat, and that's changed the value, and that can change the parameters in your system model. Maybe the storm that you measured had one line, a significant line that was out of service at the time. You need to make sure that the system model all matches the conditions during which you've measured your magnetic field. That can clear up a lot of first order issues. Then having the next thing to go is the magnetic field. Magnetic field needs to be accurate in intensity and in direction. Direction's hard unless you're getting magnetic field information that's relatively close to your GIC monitor. So use a local magnetometer if possible. Make sure you have good data. And the third is local geologic complexities. So if you're in a really complicated area, think mountain ranges. Think anywhere there's complex geology, Maine. Any place like that, you may need to look into more advanced ways of calculating the electric field from your magnetic field. And a lot of this is again referenced in that report. So here are a few resources. The references I mentioned. Again, if you have any questions on this, I'm happy to help as much as I can, or try to point you in the right direction. So feel free to reach out. And now that we've had enough of regulatory compliance, I'm going to hand it off to Ludo to talk about oil and gas directional drilling.
Thanks, Jenn. So I'll finish off after we've talked about the power networks. There is another industry which is affected by sudden changes in the magnetic field, and that's the oil and gas with directional drilling applications. So when directional drilling is being used, the drilling tool use a magnetometer in general to determine the azimuth and the inclination of the drilling bits and the well. So that relies on the Earth magnetic field measurement, so DC measurement. So if there are sudden changes in the Earth field, all of a sudden our directional informations are going to be erroneous for a period of time. So having local ground magnetometer data can help in determining periods of disturbances, but also determining whether the errors or the changes that you are seeing are linked to a fault in the sensor itself, or if it's an environmental disturbance due to electromagnetic storm, for example. And like for the power network, it is quite essential to have proximity between the reference magnetometer and your drilling sites. You don't want to use data that has been acquired 1,000 kilometers away, because geomagnetic storm impact can change locally, and as you travel further south away from the poles, the amplitude of the disturbances will be in general less. So you don't want to use data that come from a sensor too far away. So if we look at the impact that it can have, typically in directional drilling applications, sensors try to achieve precision of about 50 nanotesla and an angular accuracy in the range of about 0.1 degree. Now, if we look at the effect that a geomagnetic storm can have, we can see hundreds of nanotesla change in field over periods of few hours or few days. And that can translate in change in declination or inclination by 0.2 to 0.5 degrees. So what will that do on your directional drilling tool is it will increase your ellipse of uncertainty on your well. So the area where you think your well is, that error will greatly increase. And that can have some downside to it. It can increase the risk of collision with other wells in the environment, or it can get you to reach your target reservoir in a less than ideal angle, which would reduce production rates for that particular well. So that can have some detrimental effects for the directional drilling. Another application to consider in the oil and gas is magnetic ranging. And that's the method used to position wells in close proximity to one another, or to intersect multiple wells, for example. And there's two core techniques, one which uses an active magnetic source, and because that's an AC signal that is less sensitive to geomagnetic storms. But there is also use of passive ranging, which use the metallic casing of a well as your target, and then the regular directional drilling magnetometer to measure the field, and that is a purely DC field measurement. And that will be greatly impacted by geomagnetic storms, as you can see, get different field induced in your casing and errors on your directional information coming from your magnetometer downhole. So where external magnetic data can help is to give you an idea of the background field changes and how bad the field is changing for a period of time. So that information could be used as a go, no go for your drilling operation. It's not ideal to lose production or drilling for a few hours or a few days, but it's better this than having bad data and bad direction information. Or alternatively, if you have close proximity data, you might be able to improve and to correct for the variation that you are seeing on the directional magnetometer. So as mentioned, the proximity of the reference magnetometer to your drilling site is important. On the left, I've got the map from Intermagnet of the observatories located in North America. And as you can see, they are well distributed, but there are some gaps, especially in the US Midwest, where there is very little presence of observatory standard magnetometers. On the other hand, you have the MagStar network, where you have sensors that have been located in the Midwest and which end up being in fairly close proximity to some of the main drilling operations in Oklahoma, for example, or in Texas. And that would give you access to local data that could be used to feed into daily data drilling operations. So that's something to keep in mind to add to the quality process for the oil and gas. So now, what is going to be the next step with the system? And as Jenn mentioned, measuring magnetic field with current could be quite a good complement. And GMW offers quite a range of current transducers, Hall effect current transducers, which could easily be retrofitted onto transformers to do a direct GIC measurement in addition to the magnetic measurement. So there are either slip-on or clip-on models that could be easily added to conductors and provide that GIC information in addition to the magnetic data. So that's something that will be explored and see how it could be implemented in the future. And that leaves us to the end of the presentation. So if you have any question, please ask, and I'll pass over to Ben now.
Thank you, Ludo. Give me just a moment to see what questions have come in. So just a moment here. Okay, we did get one question earlier asking what technology is available for monitoring. I think that was asked pretty early, and I think we've covered that fairly well. But the second part of that question is, how frequently is the data saved? I think that's a good question for you, Mike.
So for the MagStar system, every top of second, the sample for that second is transmitted over the cellular link or over the wireless link, and it is sent to a server on the internet, which is actually in the cloud. So the data is immediately sent to disk right then. So it's really a direct transmission to the database every second.
Okay, let's see. We have a little bit more time, so does anybody else have any questions for either Ludo, Jenn, or Mike here? Otherwise, I'll give you your time back, but we'll wait just a moment to see if anything comes in.
I think we had one come in on chat, Ben.
Oh, I missed the chat. Thank you. That's a good point. Perfect. What cadence is the MagDAR stated sampled at? Well, I think we just got that, right? That it's continuous at about 1 second is what you said, right, Mike?
That's correct. It's 1 hertz.
1 hertz. Okay, perfect. And do we have any other questions? All right, well, of course, you can reach out to any of us by email afterwards. We will follow up with a recording later this week, and as well as the slides, and all our contact information is in there. So again, I hope this was useful to you, and have a good day, everyone, and stay safe. Thank you.